Now let's apply this torsion equation to study some problems. Okay, the first problem that I am interested is in the following. I have this bar fixed at one end, the torsion applied at the other end, and the cross section is a circular cross section. This is x and this is y. Okay, now I want to find what are the stresses. Find the, in particular I want to find the shear stress in the cross section and angle of twist of a section at a distance L from the support, from the fixed support. Okay, so this is what I am interested in finding. So to find the shear stresses, I have to first find the polar moment of inertia. Torsion is given as T, so I have to use this equation to find the shear stresses in the cross section. Okay, so to find the polar moment of inertia, J is integral r square dAz AZ. Now for the circle I can use the polar integration. So basically xy, I have an area. This area is given by, this length is dr and this length is r d theta, but theta is measured from here to there. Okay, so dAz would be integral Az r square r d theta into dr. Okay, where the limits of integration would be 0 to 2 pi for theta and 0 to r, where r is this radius of the circle, r, okay, of the radius of the circle. So this will be theta integrates to 2 pi and r integrates to r power 4 by 4. So this is pi r power 4 by 2. Okay, so my shear stress expression becomes T by J into r, the radial location. So that will be T by 2T by pi r power 4 into r. Okay, so now let's see how this variation of the shear stress occurs in the cross section. Okay, so I have this cross section which I have zoomed out. Okay, so the center of the cross section is this x, this is y. I know that the shear stress is varying linearly radially. Okay, which means at the center where r is 0, the shear stress is 0 here, and then if I look at some radial distance r here, the shear stress is going to vary linearly, that is going to vary something like that. It's going to vary linearly like that. The magnitude is going to increase linearly from the origin to maximum at the periphery. Okay, where this maximum tau max would be 2t by pi r cube, because r is the outer radius now. Okay, so it varies linearly from 0 to 2 pi by 2t by pi r cube. Okay, now what is the orientation of this? Here I drew it inclined. Why did I do that? Because now what I have is the magnitude of the shear stress, but the direction of the shear stress will vary depending upon the location, because there is sigma xz and sigma yz component coming in here. Because of this sigma xz and yz component being there, it will vary, the direction will vary. The magnitude of shear stress will remain the same at a given radial distance, but the magnitude will vary depending upon its x and y location. in particular when y is 0, let me rewrite that expression that we had before. You add sigma xz as minus t by j into y, and sigma yz is t by j into x, right? Okay. Now in particular when y is 0, for example when I am on the x axis, the shear stress will vary. There will be only sigma yz shear stress. This is a sigma yz shear stress, and this is very linearly like that. Okay. And when I am at x equal to 0 line, which is a y axis, I will have only sigma xz coming in. There will be only sigma xz coming in, and the shear stress will vary linearly like this along that line. Okay. On an inclined line, when there is both x and y, the variation will depend upon what x and y values are, and it will be tangential to the point, the circle at that point. Okay, that's how it will be, and hence you get the variation of tau along an inclined line to be as shown here. This will be the direction of the tau in an inclined line with the arbitrary x and y directions. Okay. Now let us see what happens when the cross section becomes an annular cylinder cross section. Okay. If the cross section becomes an annular cylinder, that is, okay, for annular cylinder cross section as shown here, say this is x, y, and the dimensions of the cross section is Ri inner surface radius, R0 is the outer surface radius. Now all the things remain the same except that now j becomes pi by 2 Ri power R0 power 4 minus Ri power 4. Okay. The integration is the same except that the limits for r becomes Ri to R0 instead of 0 to r. Okay. And hence you get j to be different, all the other arguments remain the same. The variation of the stresses will be in the region where the material is. The variation of the stresses will be in the region where the material is, that is only along this thickness region there will be shear stresses developed. Okay. Okay. Now coming to the second part of the question, how does the angle of twist vary along what is the angle of twist at a section L from the fixed end? Now for that we have to use the second part of this equation, T by j equal to shear modulus times angle of twist per unit length, and you have to compute that angle of twist at a cross section at a distance L. So basically omega is T by j into mu. Okay. And angle of twist is, what do you want is, you want beta, that is the angle of twist. Okay. That beta is omega times z, which is now the position of the section is at a distance L from the fixed end, so that z is L. So you want this L, so this is TL by mu j. This beta is angle of twist. Beta is the angle of twist. Okay. So we found the angle of twist and we found the stresses. So you know what is the rotation that the cross section undergoes and what are the stresses that are developed in the cross section. Okay. Next let us do one more problem, wherein now what I have is, wherein I am applying a torque T in a step shaft like this. Okay. Now let us assume that this has J1 as a polar moment of inertia, this has a length L1 and mu 1 is the shear modulus of this material. Let us assume this as having a length L2, J2 and mu 2 are the polar moment of inertia and the shear modulus of this second shaft. Let us also assume that this is A, B and C. I am interested in finding what is the torque diagram and angle of twist diagram. I am interested in finding these two. Okay. Now, for this I know I have applied a torque T. This is a statically indeterminate problem because there are two fixed chains. Draw the free body diagram of the structure. There is a torque T as a torque T applied here. There will be a reaction torque T c there, and there will be a reaction torque T a here. Okay. Further separating out these blocks, I will have T c acting here. So, to maintain equilibrium there will be a T c acting like this, and here there is a T and a T c opposing that, because T c has to equilibrate there, and then there will be a T a acting like this. Okay. T a acting like that. Okay. So, in this member, effectively in member A B, the effective torque in member A B is torque in A B is T minus T c, and torque in B c is T c. Okay. So, A is fixed. So, how does the angle of twist vary? Angle of twist will vary from here. In this member, the angle of twist is going to vary like this. This end is fixed, A is fixed. So, the angle of twist is going to vary linearly like this, where this value will be given by T minus T c by J 1 into L 1, okay, mu 1. Okay. And now this end is fixed. So, basically in this section it should vary here, the angle of twist at this end C, this end B, the angle of twist at the end B is the same as this value T minus T c L 1 by J 1 mu 1, and then this T c is opposing that angle of twist. This angle of twist is anticlockwise, T c causes the clockwise rotation. So, it will decrease down to 0 because that end is fixed in there. Okay. And this slope of decrease is given by the slope of this decreasing function is given by T minus T c to L 1 by J 1 mu 1 minus T c into Z by J 2 mu 2. Okay. Z, if I am measuring Z from A, it will be Z minus L 1, okay, Z minus L 1. Okay. Now, I know that C, the twist has to be 0. I use that condition to find what T c is. Okay. So, twist at C, angle of twist at C is given by T minus T c to L 1 by J 1 mu 1 minus T c by J 2 mu 2 into L 1 plus L 2 minus L 1 must be equal to 0. Okay. So, that gives you T c into L 1 by J 1 mu 1 plus L 2 by J 2 mu 2 must be equal to T into L 1 by J 1 mu 1, right. Okay. So, that gives me T c to be T into L 1 by J 1 mu 1 into L 1 by J 1 mu 1 plus L 2 by J 2 mu 2. Okay. So, we have drawn the angle of twist diagram here, combining these two you will get the angle of combining these two diagrams, superposing these two you will get the angle of twist diagram for the entire member. Now, angle of twist diagram would be the following, the torsion diagram would be the following. The torsion diagram would be the following. In this member there is a negative torsion T c, there is a negative torsion T c, and here there is T minus T c in there. Okay. So, basically this is the torsion diagram for this structure which is fixed at both the ends. Okay. Okay. So, what you have seen is you have seen how to analyze for twisting of a closed section in this class. We worked out two solved problems, one of a one end fixed, the torsion applied at the other end, and the second problem is a step shaft which is fixed at both the ends. Okay. Thank you.